it lacks measurable indicators of progress. Like, okay, what's step 1? Maybe find all the features. Step 2, find all the circuits, and then step 3, find all the patterns. But like, how do you know how many you found? There's a bit of compatibility issues. I can talk about that a little bit. And I think fixing a language pretty early on can also be a bad thing, right? So, yeah, I think this is like slide 8 or 9 now. But yeah, this is kind of the operational pipeline of this parable of biology. Step 1, find all the features. And I'm going to flip back and forth between the tabs. You can't see it, but I can, just to see if anyone has questions or comments. Step 1, find all the features, thoroughly understand each of them in a vacuum. Step 2, understand feature construction and computation. That's the circuits part. And then step 3, characterize all motifs, all the high-level patterns. The still circuits thread kind of did each one of these a little bit. I did look at the past talk by Kurt Tiggs, and I thought it touched on a lot of things. One comment early on that I kind of disagree with is this whole thing of paradigms change frequently. And he talked about how in the beginning there was like early circuits doing patching manually and then AC/DC and stuff like that. Then we did neuron labeling and then sparse dictionary learning, and then there's some alternatives, and then now we've got attribution graphs. But all of these are really sub-paradigms of the feature biology perspective, right? Like all of these are really considering features as directions, features as neurons, features as attention heads. Like maybe this is like less well known, but the fact that you can even label an attention head as an induction head or as a previous token head means you're implying that that attention head is monosemantic. It has a sole purpose, and the sole purpose is this label, right? And so it is a feature, right? And you make graphs out of these features. The graph has changed now to these sparse features, and maybe now they're going away. But this is all still kind of within the realm and within the language of this like biology parable, right? So, and then you can say, oh, what about SLT? What about singular learning theory? What about attribution parameter decomposition, right? One person could say, oh, that's a different paradigm. I don't think that's super useful. I think, ideally you should be able to talk about things in the same place. I think SLT and APD, they're like more of like agendas, and they're more like, approaches to solving a field. But, compatibility wise, I think you should be able to reason about them both in the same place. So, how to build your own moral compass. This is the skill you guys need, okay? And this is what research taste is you have a moral compass. You read a paper and you're like, does my moral compass say that this is like legit? Right? And here's the operational pipeline. First, you describe, and hopefully this is like operational, like hopefully you can kind of do it on your own. I'm going to run through an exercise as well. So step 1, describe what extremely strong success looks like. Right? So like beyond a shadow of doubt, what would be absolutely insane if true? Okay, so you don't need to really look into the weeds much on how mechanistic interpretability is built or stuff like that, but you just want some really strong criteria for what would be great if true. And then step 2, break this into a set of criteria. North Star criteria, like, oh, we would need to really, really nail this thing out for this to be possible, and we would need to nail this other thing out for this to be possible. And you have this like full covering set of criteria, and then step 3 is you evaluate any past, present, and future method along these criteria. These are the dimensions of progress. Okay? There's some cool comments in here. Esben, I think SLT would say it's a different perspective by constructing the learning parameter over a learned space. Okay, let's and then Renee, I agree with you for the paradigms changing frequently. Should I answer these now or later? Esben, what's your take?
Yeah, you can.
Q&A. Okay.
You can choose to. Yeah, you can choose to answer it towards the end. Yeah.
Okay, sounds good. Cool. Let's run through this. A worked example. Describe what extremely strong success looks like. In quotes, fully understand how computation works in any model, train across any task, and predict any behavior out of distribution. It's pretty strong. I don't think it's even possible, but it certainly is strong, right? It's certainly a strong criteria, and it certainly, beyond a shadow of doubt, would be really big if true and possible. Okay, so that's an example of what extremely strong success looks like. Now let's break this into a set of North Star criteria. Okay, so fully understand how computation works. So we need to be our understanding to be really, really strong. Maybe that understanding is beyond our knowledge, so maybe it's like verifiably good enough. We have some way to verify that our understanding is good enough. No interpretability illusions. What does that mean? I don't know. Maybe Stephen Casper comes in with his mech-interp engineer sequence part 2, and he rips a million holes in the current modern state of mech-interp, and the thing completely avoids all of them, right? And then we have our circuits, and they predict things in distribution, but it also predicts everything out of distribution. Okay, so here's a set of criteria. Okay, so it works on any model, in particular any future architecture, right? So maybe right now we have transformers, and maybe AGI will be also a transformer, maybe it won't be. Maybe it doesn't have to be fully architecture agnostic, but it just has to work on all the ones that will be there in the future, right? So some restrained scope of architectures that will be relevant. It has to have, verifiably good understanding. CAS can't rip a hole in it. It handles everything in distribution, handles everything out of distribution. Data agnostic, kind of works on any kind of data, and therefore any kind of task. Okay. And now we can evaluate methods along these criteria. Let's pick one, sparse dictionary learning. That's a really popular one, right? So let's think about it. It works in distribution. That's great because it's trained on data and it reconstructs that data, right? So anything that's in distribution, hopefully it'll work for there. It's how about like architecture future proofing? I think it's been listed before that it kind of depends on where you put the SAE, but strictly speaking, it decomposes in activation space, and it doesn't really matter where you get it from. So I would say it's fairly architecture agnostic, and that's a good win. A downside is that it does not work out of distribution at all, right? Or at least it's not proven that it can. I think there's a lot of case studies that show that it does not work out of distribution, and in principle, it should not, right? You train it on a very specific data distribution, and so it should reconstruct that precise data distribution. But once you are out of distribution, then you're out of the distribution that the SAE is trained on, and you're out of distribution on the model. So there's like two composed things that you're out for. And it's really going to mess with your reconstruction. SLT, they really want to focus on decomposing on the data side or something else, right? But you can apply this to, I don't have a slide for it, but you can apply this to other things, right? You can talk about, in the past we did patching, manual patching, circuits and stuff like that. We would pick a very narrow task distribution, right? So we would pick like interpretability in the wild. That was like the indirect object identification, and so that was like very not data agnostic. It really depends on being in a very, very specific thing, and it was also very architecture agnostic, architecture dependent, right? So doesn't, and yeah. So maybe I'm just rambling right now, but we can continue. Where should I go? There's a taxonomy. Okay, this is a slide from a while ago, actually. So you can look to how I should do this talk at this point. Sorry, I didn't prepare a whole lot. I'm just on vacation. Here's an example of a perspective, right? Ideally, our interpretability methods are like fully data independent and fully architecture independent, right? Earlier, circuit analysis is highly data dependent and highly architecture dependent. At least manual circuit analysis is. SAEs and transcoders, they have low architecture dependence, but still high data dependence. and it seems impossible to address anything out of distribution. So maybe a weight-based only approach could work. That would make it data agnostic. Maybe into directions in the loss landscape or in parameter space. That would be sort of architecture agnostic. That's kind of what the APD or SLT people are trying to do. And maybe try to do both. Barriers to execution. It's actually really, really hard to come up with new ideas in his place. It kind of does require a lot of research taste to be able to kind of carve out completely new agendas. What else can you do? Here's a thing actually I made almost a year and a half ago. Solving mechinterp kind of involves filling out this ternary plot. You can kind of here I made kind of like 3 kind of dimensions. I can say like, oh, you can understand things on a microscopic level, you can understand things on a macroscopic, and then you can understand things on a training dynamics level. And you can sort of plot different papers, and you can fill out this sort of plot. And this, I kind of used this before as like a way to sort of identify gaps in the literature. So this is kind of from the previous taxonomy that I skipped over. You know, microscopic to macroscopic is kind of a conflation of a lot of different things. Here's a labeling of it, right? So this is like 2 years old by now. I'm sure we could fill out a lot more of this. But yeah, I kind of wanted to label more for this talk, but I kind of ran out of time. Yeah, I think that's the end of this talk. I hope you got something out of it. And sorry for letting it ramble near the end. Source me always works well.
Yeah, amazing. Thank you so much, Alice, for putting this together. Honestly, I always love the visualization slides because they put like mechanistic into such good perspective. I'm wondering if folks have some questions or thoughts. I think someone said they agree upon the paradigms changing frequently lens from yesterday's talk, sort of like early circuits to neurons to SDL to alternatives to attribution graphs. Given what has been discovered through circuit mechanistic research, do you think we could still be wrong in understanding how neural networks work past mathematically, given still mysterious topics of multi-dimensionality and superposition?
Oh gosh, Renee's a speaker as well too now.
Oh, okay, awesome. Yeah,
Um,
sorry, Renee, I just read out your whole comment, but feel free to give another stab at it. Yeah.
No problem. Just thanks, Alice, for the great talk, and yeah, keen to hear your thoughts.
yeah, so I think we could still be wrong. Okay. I think multidimensionality and superposition. This is possibly a very, very hot take. But I think superposition is kind of a really bad misnomer. It's not clear whether. How should I state this? It's been a while. Usually I try to think of like different perspectives, like different paradigms. So like right now the main paradigm is like features or directions, and now people are talking about if there's multi-dimensional features or stuff like that. I try to think of these as like we have a theory of neural networks, and we're trying to update this theory. And right now, what we have is something like Newton's law of gravity or something like that. It's like a relatively simple description of a pretty complicated world, and its precision is like pretty good. We now know that it's not literally exactly true, but it's good up to a point, right? And then it would be crazy, absolutely crazy, if Newton's law of gravity literally was the solution to everything in the universe, right? But what we have is a theory, and depending on how precise we need our understanding to be, we can kind of augment this with new kinds of perspectives. And it's not really about being wrong, right? It's about kind of not being precise enough to describe the things you need to describe. We now know, or I don't know if we now know, but people are starting to disagree, let's put it that way, on whether certain methods, one being sparse dictionary learning, is like robust enough to accomplish the things that we want it to accomplish. So now like DeepMind, for example, is kind of like laying off of sparse dictionary learning, and Anthropic is kind of going all in on it. It's no, I lost my train of thought. But
Yeah, no problem. I think that what you're saying is correct though, because I guess in a sense we're always wrong depending on how you define it. If you include completeness of understanding something, like in order to categorize fragments for human understanding, we're wrong probably with everything. But it's just like, what are we correct enough to move forward? And just like you said with Newton's gravity law, and then further understanding that we gained, it was useful for so long to get us to move forward. So obviously, it's just tricky in such a new field where key understandings that shape the efforts of a very small group of people could really affect the kind of progress that we can make. But I think just kind of like accepting these what is for now the ground truths and building on that rather than committing too much energy at this stage to proving them wrong or potentially exploring them, or at least I'm too scared to take that path.
yeah. I think at least at this point, maybe one useful thing to say is that like I don't like at this point it doesn't seem super useful anymore. Oh man, I hope I don't get hope this isn't my downfall. I get cited and I get rejected by Anthropic or something because I say this. But like doesn't seem as important anymore to find specific counterexamples of like feature geometry or something like that. If we're starting to like be less all in on it collectively, then finding specific counterexamples is like less crucial because people are less invested in general. I don't know. People are typing.
People are typing. Thank you so much,
No.
Alice, for the talk as well. Really fun to hear. I think there's also a question of like, do you think the current paradigms sort of cover what we need to cover, since it's all to some degree just different ways to try to engineer this reverse engineering process? Like, do you think there's something completely missing? And then do you think organizations like Goodfire and these massive investments directly into interpretability will change this drastically for open source science as well?
Mm. I think like they were certainly in a better place than we were before. Like nowadays, like I couldn't see all of the slides from Kurt, but he listed out a bunch of like frontier kind of like problem areas. I think like not all of these problem areas are like tractable. Because sometimes you pick a problem area and then you say, okay, it would be great to like mechinterp some of this. But like whatever mechinterp is feasible, like whatever mechinterp you can accomplish by throwing at it ends up like not being actually like operationally useful. Like okay, we understood when the model knows what it knows or something like that. It's like okay, cool. Now what? And then not being able to answer the question. I think probably I don't know. I think we're probably pretty good on it. I think more investment into non like biology framework things is kind of what we needed for past year. We're starting now, which is good. But I don't think we necessarily need more paradigms. Like more like fundamental kinds of agendas. We can kind of just like pick small things and chip off things without necessarily needing to be aligned with one kind of thing.
Yep.
I don't know if that's helpful.
No, I think it makes a lot of sense. I think it's also a question of like what comes after we've reverse engineered the networks, and what is the like what are we taking with us? Like, are we steering the models now? Are we what are we deploying these millions of dollars to solving? Is it putting them in a better spot for us to?
Yeah, exactly.
Yeah.
Yeah, I mean, like one open question that is often like not thought of enough, I guess, is like, okay, we could like apply this mechanistic understanding to steer, but it's not clear whether we needed this mechanistic understanding in the first place. We could have just steered.
Yeah, exactly.
Right. Or like you can find unsupervised features, and you can find features in an unsupervised way. But it's not clear like what value, if any, you would get out of finding the circuit that leads to it.
Yeah, and I think there's another question there also from just circuit reverse engineering in general. Like if you take like literal IC integrated circuit reverse engineering, where they I've been doing neuroscience, right? And in neuroscience you have like you try to reverse engineer how the causal structures in the brain work. And then they try to use all the same methods on integrated circuit, and they could not at all, like they couldn't use it for anything. So it's all these ways of cognitive neuroscience and so on. And so there's both a question of like this, whether the current methods used of like circuit analysis and so on, and automated construction of these causal patterns for specific behaviors, they truly get to the underlying point, like apropos superposition, right? Apropos functions that are embedded across many neurons or something like this. And whether we need something something that looks more like even more verifiable in a way. Like if it's like Philip Quirk's research, who's with Martin, on this question of constructed circuits embedded into neural networks, I think is one answer to that. But I guess like SAEs and the other parts of it are like less directly answers to it right now.
Yeah. Okay. I'll give one last hot take, I guess. So I think the last hot take is, so I wrote down on paper at least kind of like some of the frontier problem areas that Kurt enumerated in the second half of this talk. So some of them are like kind of like discovery, kind of like biology, reasoning, self-knowledge, chain of thought, faithfulness, model diffing, universality, debugging, and applications, sort of like activation monitoring, kind of model extracting knowledge, red-blue kind of settings, steganography capabilities. My hot take is that you do not need a universal language to contextualize all of these different things. You can just tackle these problems with different approaches to every single one of them, which is a win for the individual. You can just kind of use different approaches to try to tackle these things, and you don't need to call things features, and you don't have to force your way and use SAEs to do it. You can kind of just tailor your own custom approach to making progress on any one of these to be able to do useful things. So you don't have to like take the features, circuits, and motifs approach to getting that done. You can kind of just hack your own way through it and do it the other way around, I guess. And that makes it easier, at least, to make progress on those problems. And yeah, I think it's like tailoring your approach to the problem you need to solve, rather than having a language wide enough to cover it, makes progress easier.
Yes. Okay. Wonderful. Great points. And I think hot takes on mechanistic interpretability are always fun. There's a lot of stuff to talk